Okay, good morning, dear colleagues. Today we will continue with our course Basics of Nuclear Chemistry. And today will be the third lecture and with very important topic related to interactions of ionizing radiation with matter. We will talk about interactions of electrons, alpha particles, photons, means gamma quanta, and neutrons with matter. It is important because, first of all, the interaction of ionizing radiation determines the effects of ionizing radiation both in, let's say, materials and living organisms. It is important for construction materials and for radiation protection of the workers, of the staff, of the medical personnel, and for many other things. So, we will start just with the determination or that there are two different types of interactions. First is elastic. We will not talk about it today for a lot because elastic interactions is just the change in momentum of the ionizing radiation. So if electrons come to the material and just changed its direction without giving the energy to the material, it's elastic interaction and there is no ionization. But inelastic interactions, interactions that we are interested in, it is for ionizing radiation, it is change in momentum, in energy, in charge, and for the material itself, there are two different consequences of interaction. It is excitation. That means that there is change in the energy of the atoms and molecules. So they change the energy level. That means that after excitation there is a relaxation with the emission of characteristic X-rays or characteristic visible light. And that is maybe more important for us, it is ionization. So ionization means that there is a release of electron from the atom or a molecule, and thus there are charges formed during these interactions. So if the energy that is transferred to the matter is less than energy of ionization, then there is only excitation because there is not enough energy to ionize matter. And if this energy that is transferred to the material is higher than the energy potential, then the ionization can occur. And we will start with the heavy charged particles. And heavy charged particles for us, the most important is alpha particles. But when we speak about heavy charged particles, we mean that it can be protons and all the particles that have masses higher than mass or larger than mass of the proton. So it's proton, neutrons, alpha particles, other nucleus of the other elements, carbon, nitrogen, and others. And what is the consequences of the interaction of heavy charged particles with matter? First of all, we should look on this quite huge equation formula named after Bethe and Bloch, and we will not look deeply on this equation, but what is important from this formula, that for heavy charged particles there is no effect of the mass of these particles, but there is effect of the charge of the particle, here it is, squared charge, and the energy or speed of the particle, so it is beta here. And when we look how the heavy charged particles are moving through the media, through the matter, we can see that the trajectory it is straight line. There is almost no scattering of these particles because, again, they are heavy charged. And when we speak about the interactions, I will go back a little bit. You can see that the most important parameter, will it be ionization or excitation, is the energy of ionization or ionization potential. And that means that all the particles, they interact with the electrons of the atoms and molecules. So they not interact with nucleus. They interact with nucleus, but in very rare events. Because if we remember, just a small reminder, that the nucleus is only 1/10,000th part of the atom. Thus, it's a very rare event when two particles can then the particle can move to the nucleus directly. So it will usually go in some space near the nucleus, but it is a very rare event to collide of these two particles. Thus, the main way of interaction it is interaction with electrons of the atomic orbitals, atomic energy levels, etc. Thus, if we again compare the mass of electron and mass of the heavy charged particles, the difference will be 1,000 times. That means that if such a huge particle will meet electrons, it will simply it simply doesn't feel this small mass of electron. That's why the track of the heavy charged particles, it is the straight line. And again, there is two types of ionization. So the first type of ionization, called direct ionization, so alpha particles or other heavy charged particles, they have charge. It can be +1 in case of proton, for example, or +2 in the case of alpha particle. And this charge interacts with the other charged particles, electrons of the atoms and molecules. And thus, this interaction causes the secondary or induced ionization. So, these electrons that are released due to the interaction of alpha particles and the matter. So, these electrons released due to the direct action of the alpha particles, they called delta electrons, and these delta electrons, they also have quite a high energy. We can calculate the energy of the delta electrons with these equations, and we will get the energy of delta electrons equal to 100-200 electron volts, and still this energy is much higher than the energy of the ionization of the molecules and atoms. Thus, these delta electrons, again, these electrons are released due to the direct action of alpha particles. And these delta electrons have a very high energy. And thus, these delta electrons can cause the indirect ionization of matter, and this fraction of indirect ionization can have a value of 70 to 80%. So that means that the action of alpha particles, the main contribution to the ionization is caused not by the alpha particles itself, but by the secondary processes by ionization by delta electrons. So that is important, because if we will look on the track of the alpha particles, it is quite short track and very narrow. But electrons, delta electrons, they are small particles, and thus they can move to longer distances, and thus the ionization of by alpha particle will be not such a narrow track, but it will be wider, so it will be not so narrow. Okay. When we see how many particles can be ionized by alpha particles, depending on the energy of alpha particle, we will see this type of curve. That means that when the alpha particle has very high energy, it moves directly through the matter, and it is so fast that the interactions between the electrons and alpha particles is very small. That's why the losses of energy is very small by the distance. So it is the ratio of the lost energy of alpha particle divided by the distance that the alpha particle is moved. This relative energy losses, they are very small when the alpha particle is moving very fast. That means that the energy of alpha particle is very high, so the scale in mega electron volts. And when alpha particle is decelerating, it is losing its energy. And thus the interactions between electrons and alpha particles become more and more probable, and thus the energy losses become very high. And in some case, when the energy of alpha particle, means the speed of alpha particle, becomes low, it can catch first one electron. So because alpha particle has charge 2, it is nucleus of the helium-4, as we remember. Thus it can capture one electron and then the second electron. And in this case, the energy losses become very significant. And when the alpha particle captured 2 electrons, that means it doesn't have longer charge, then the interaction with electrons become very weak. And thus the energy losses goes to 0. So this means that almost all energy alpha particle loses at the end of its track, when the energy of alpha particle becomes very low. Thus, when we look on the range of the alpha particles, we can see that the flux, that means the number of alpha particles divided by the square of the matter, flux of these alpha particles almost independent on the distance before the end of the track, before the maximum range of the alpha particle. Again, all the energy of the alpha particle is lost only at the end of its track. And before this, all the alpha particle just moving through the matter almost without interaction, and at the end of their track, of their range, they lose all their energy, and thus they are captured by matter, and thus the range of the alpha particle So they have the maximum range, and the drop, this decrease in flux of the flux of the alpha particles occurred only at the end of the track, or at the end of the range of alpha particles. Again, if we will look how many alpha particles are going through the matter with the thickness lower than their maximum range, we can say that 100% of alpha particles will go through this matter. But as the thickness of the sample of the material will be around the maximum range of the alpha particles, we can say that 0% of the alpha particles will move through this material. And it is very important, especially for the medical applications, for proton therapy, or in wider term hadron therapy. That means the therapy with the accelerators which accelerate heavy charged particles. So again, we can see that all the energy, heavy charged particles, including protons, all the energy is lost only at the end of the track, of the range. And thus, all the energy, all the doses is absorbed at the end of the track of the alpha particles, or heavy charged particles. Such distribution of particles dependent on the distance, called Bragg curve, and this maximum absorption of the energy called Bragg peak. And that is more important, that after the maximum distance there is no more alpha particles or heavy charged particles or protons. And thus all the energy is absorbed in very narrow zone, or very narrow spot, and there is no charged particles that are moving in the distances longer than this maximum range. And this is not the case for the photons, for gamma quanta, for X-rays. The distributions of the absorbed dose by the X-rays have this dependence, and as you can see, there is no maximum range of absorption. Thus, if X-ray or gamma quanta goes through the matter, they absorbed by their flux just continuously decreasing, but not going to zero. And the consequences of these two types of interaction is the different distribution of the doses in the matter, in the organism of the patient. This is an example of the distribution of doses for X-ray or gamma treatment of the patient. And this is distribution of doses during the treatment by protons. So it is the model, but the model is very close to the reality. So you can see that as far as X-rays and gamma quanta, they go through the matter without the complete absorption. They generate the additional dose in the whole body. And protons, as far as they have this maximum range, they absorbed completely at a certain distance, and thus there is no additional doses in the rest of the body. That's why this hadron therapy is very promising for treatment of different diseases, because it can lower the total dose absorbed by the human body. And now we will speak about the light charged particles, electrons, and for them, again using the similar equation, we can divide this equation by two regions of the energy, so it will be a different approximation of this formula. And for slow electrons, it will have this much more simpler look. And for ultra relativistic, means for very very fast electrons, it will be also much simpler equation with this look view. And we can see that for in these equations we always have the mass of electrons. Thus, for the electrons, for these light particles, the mass become very important when we talk about the loss of energy. And we remember that the mass is not so important for heavy particles. And there is, of course, a direct interaction of electrons with other electrons in atoms and molecules. As far as the beta particles or electrons and just accelerated electrons, they have very high energy. When they collide with the other electrons, they can transfer this energy to electrons, and the electrons of the atoms and molecules will be released, and thus ionization will occur. But there are another types of interactions of electrons with the matter, and one of them is called Bremsstrahlung. It is from German word meaning the breaking Brems, and Strahlung, radiation. And thus it is a radiation that is generated due to the stopping or decelerating of electrons in the matter. We know that the particles, charged particles that are moving with acceleration or deceleration. Deceleration is the acceleration with just the negative acceleration. So the charged particles moving with acceleration will generate the electromagnetic wave. And the intensity of this, the power of this electromagnetic radiation will depend on the squared acceleration that in turn depends on mass and on the charge of the particle. So again, as we can see that the intensity of this Bremsstrahlung has a reverse dependence on the mass squared, and thus as far as the beta particles or just electrons, they have very small masses. That means that the intensity of the Bremsstrahlung will be very high. Again, if we will take the mass of protons or alpha particles or other heavy charged particles, we remember that they are 1,000 times larger, their mass, than the mass of electron. And if we will use this approximation, we can understand that the intensity of the Bremsstrahlung for these heavy charged particles will be millions times less than the intensity of Bremsstrahlung for electrons. Thus, we can neglect this stopping radiation generated by heavy particles, but we cannot neglect it in the case of electrons. So, what means the deceleration or stopping? It doesn't mean that the electrons will stop completely, but as far as they interact with other electrons of the atoms or molecules, they change their directions. Also, they change their directions due to the electrostatic interaction with the nuclei. Changing the direction, it is also acceleration for electrons. Thus, in any types of interaction of electrons with matter, they will have acceleration or negative acceleration, and they will always generate the Bremsstrahlung, this breaking radiation, and intensity of this radiation will depend both on the energy of the electron and on the charge of the matter, or effective charge of the matter with which electrons are interacting. And so that means if we will take light materials like carbon, or let's say organic materials, plastics, polymers, even aluminium, the intensity of this breaking radiation will be low. And if we will take heavy or very dense materials like lead, for example, then the intensity of radiation will be much higher. That's why when we try to stop electrons so for safety reasons, for example, we should not use the dense material, the heavy materials, but we should use light materials like plastics, aluminum, and others. The intensity of this breaking radiation has this even distribution. The spectrum is continuous. And of course, there is this characteristic radiation. This radiation is caused by the inner transfers of electrons between different energy levels. It is the same as the characteristic X-rays when we talk about the electron capture decay. So it is caused by the transfer of electrons from the higher energies to the lower levels, from higher levels to the lower levels. And we can also calculate the intensity of the breaking radiation for just mono-energetic electrons or for beta particles. For beta particles and for electrons, there is a special parameter K that is a ratio between the radiation energy losses. So it is energy losses caused by the release of this Bremsstrahlung and divided by the ionization losses. So it is losses of energy. All the energy goes directly to ionization of the matter. And the critical parameter is the K equal to 1 when the radiation energy losses become more favorable than the ionization losses of energy. And there is dependence for the lead, for example. We can see that the radiation energy losses become important at energies higher more than 1 mega electron volts, and let's say at 10 mega electron volts for accelerated electrons, that is typical for synchrotrons, for accelerators of electrons. The radiation losses become even more important than the ionization energy losses. Thus, it is very important to remember that we cannot simply stop electrons, especially with high energy, because they will generate the electromagnetic waves, not the particle flux, but the flux of electromagnetic radiation, and thus we have to take additional actions to stop the electromagnetic radiation for safe operation of such facilities. Another type of interaction of electrons with matter, it is Cherenkov radiation or Cherenkov-Vavilov radiation. This radiation occurs when the velocity of the electron or charged particle is higher than the speed of light in the matter. We know that the speed of light is the maximum speed when we are talking about the vacuum. but it is not the case when we speak about the matter. And the speed of light depends on the refractive index of the material by this simple equation. So C, it is the speed of light in vacuum, and it decreases when light is going through the matter. And for particles, that means that they can have energy or velocity, and velocity will be higher than the larger than the velocity of the light. And for electrons, it means that the energy is only 267 kilo electron volts, and for many radionuclides, beta-emitting radionuclides, they have a maximum of the beta particles with much higher energy than this border value of energy. Thus, just the natural radionuclides can emit, so already the natural radionuclides can emit beta particles with the energy that is higher than this border energy for producing the Cherenkov radiation. And Cherenkov radiation itself is just the emission of electromagnetic waves in the range of visible light. So all this blue glowing around the nuclear reactors, this blue or blue-violet glowing is the release of the light by beta particles that are moving faster than the speed than the light in the water. So for water, yeah, this energy, and you can see that there are a lot of radionuclides that can emit such a high beta particles. And the nature of this effect can be simply explained, maybe not very correctly, but to understand it is in an easy way, that it is a shock wave that is produced by the particles that is going faster than the light in this matter. When we talk about the sound, for example, like in the case of this aircraft or the bullet, we can see the formation of these sound waves. Then the object is moving faster than the velocity of sound in the matter. So it is more or less the same in the case of light. If the object is moving faster than the light in the media, then the shock wave will be generated, and in the case of light, the shock wave will be in form of light. This is also an example of just a ship that is going on the water, on the surface of water, and the speed of this ship is larger than the speed of waves on the surface of this reservoir, water reservoir. And you can see the generation more or less of the same shock wave. So again, it is the simple explanation, simple visualization why this Cherenkov-Vavilov radiation is generated. Yeah, you can see it. And there is a picture just to explain you that all the energy visualization by movies, by cartoons, they usually use the green light to show some radioactive materials, but it is more correctly to show them as blue glowing objects, blue colored. And electrons, as far as they are very light particles, for them the scattering is very important. There is again a simplified equation for average angle of multiscattering. And you can see that it depends on the charge of the particle. So for protons, for alpha particles, for electrons, charge is +1 or +2. Thus, it's not such a big dependence. But there is also charge of the target nucleus, or the average charge of the matter. And thus you can see that the heavier or the more dense the material, the higher the average angle of multiscattering. This is impulse or movement of the particle and the speed of the particle. And I remind you that impulse, it is the multiplication of mass and the velocity. Thus, the less the mass, the larger will be the average angle of multiscattering. Again, electrons, they are light particles with the low mass, and that's why for them the average angle of multiscattering will be very high. And of course, the thicker the material, the larger the average angle of multiscattering, because these scattering events they occur more often in the thicker material than in the thin material. And thus, when we see the track of the beta particles or electrons, it will be also not just a straight line, but this, let's say, curve with multiscattering. For alpha particles, I said that all the alpha particles, they are moving straight forward, and they stopped, almost all the alpha particles stopped at the same distance. It's break curve. It's not the case for electrons and beta particles, because as far as they have multiscattering, and for different electrons this angle of average angle of multiscattering will be different. The loss of the electrons is not so they have not the only one distance. Different electrons are stopping at different distances, and thus the flux of electrons is changing with the distance of the movement through the matter. The longer the distance, the less and less electrons is still moving through the matter, and thus the flux of the electrons is decreasing with the thickness of the material. And electrons also, as heavy charged particles, they also have some maximum range of their movement through the matter. More or less it is true for beta particles. The difference between electrons and the beta particles, that the electrons, when we just say electrons, we mean that they at the beginning all these electrons have the same energy, so it's monoenergetic electrons. And when we talk about the beta particles, we remember that their energy spectrum is it's not a discrete spectrum, but it's some curve, and thus even at the beginning different beta particles have different energy, and their flux, it's not a straight line as in the case of electrons, but it is a curve that in the beginning can be expressed as the exponential decrease, but then it's not really exponential, but for every for beta particles this dependence is determined experimentally. But in the beginning, let's say when the length of this pathway is less than 1/3 of the maximum range, it can be expressed simply exponentially. But again, both for electrons and for beta particles, there is a maximum range of their movement through the matter. And just for example, there is a table with effective distances or a range of electrons in different materials. You can see that the dense the material, the less the distance of the electrons of their movement through the matter. And but we should remember that the higher the charge of the matter, average charge of the matter, the more intense Bremsstrahlung will be generated. So don't forget about it. And when we talk about the ionizing radiation and we talk about the beta particles, we should remember that it is not only beta minus particles, electrons, but it is also beta plus particles, means positrons. And positrons, when they're just released, they have very high energy. Their interaction with matter is the same as the interaction of electrons with matter. But when beta plus particles, when positrons are decelerating at some range, at some distance, they can have such a low energy that they can interact with electrons and annihilate. During the annihilation, two photons with the energy of 511 kilo-electron-volts is generated, and the angle between them is 180 degrees. So positrons, again, the interaction at the beginning with the interaction with matter in the beginning of the pathway is the same as for beta minus particles, for electrons, but at the end of the range they annihilate by interaction with the electrons of the matter, generating the electromagnetic radiation. And the next is interactions of electromagnetic radiation with matter, means gamma radiation when we talk about the decays, or it can be X-rays, characteristic X-rays, or generated X-ray, or Bremsstrahlung, or these two gamma quanta generated by annihilation of positrons. Thus, electromagnetic radiation is a very broad range of different radiations. So this electromagnetic radiation has no charge, no mass, and that's why electromagnetic radiation can go through the matter with very low level of interactions. But there are three main types of interaction of highly energetic electromagnetic radiation. Let's call it just gamma radiation for simplification. And these three main types of interaction is the photoelectric effect, Compton scattering, and electron-positron pair production. So photoelectric effect. That means that the all energy of gamma quantum will be transferred to the electron in the inner shell of the atom. So all this energy is captured by this electron, and of course, as far as the energy of electron now is very high, the electron is released through the atom. The cross section, so the probability of such an effect when the whole energy of the gamma quanta is completely captured by the electron, depends on the charge of the matter in the degree of 5, and it depends on the energy of the gamma quant, on the initial gamma quant. And you can see also that there is some specific peaks in this cross section, And these resonance peaks, their energy is related to the energy of the binding of the electrons inside the atom. So it is simply the energy levels of electronic shells in the atom. Okay. And as far as the electron from the inner shell is released, thus there is a vacancy now in the inner shell. And again, as in the case of electron capture, there are two different types of the consequences of this type of interaction. First is the irradiation of characteristic X-rays. We remember that then the electron goes from the higher energy level to the lower energy level in the atom. It emits electromagnetic radiation with the energy that is equal to the energy of the difference in energy between these two levels. Thus, when the gamma quanta interacts with the electrons by photoelectric effect, there is additional emission of gamma radiation, X-ray radiation, with the energy equal to the difference of this energy level of the atom. And this difference is a characteristic parameter for a certain element. Thus, we can use this photoelectric effect to analyze the chemical composition of the matter. And this method is called X-ray fluorescence analysis, is widely used for chemical analysis of the different materials. Now you can understand how it works. Again, it is based on the photoelectric effect or the interaction of electromagnetic radiation, for example, X-rays or gamma rays, and then by analyzing the energy of the released characteristic X-rays. Another type of the consequences is the transfer of the energy that is released due to the relaxation of this electron. This energy, excess of energy, can be absorbed by the electrons that are located at levels that are located higher. And these electrons at higher levels, they have lower binding energy with the nucleus in atom, and thus this difference in these two energy levels will be enough for these electrons to be released. So another secondary process is the emission of the so-called Auger electrons. So it is again the same as for electron capture consequences, and the energy of these Auger electrons again depends on the element itself, but also on the valence state or oxidation state and the local surroundings of the atom. So this method of the analysis of the energy of the released Auger electrons can be used also for determination of chemical composition, but also for determination of the valence state, local surrounding of the atom. So it's a very useful technique for chemical analysis. Another type of interaction of gamma radiation with matter is the Compton scattering. In this case, not the whole energy of the gamma quanta is transferred to the electron, but part of this energy is emitted as gamma quanta with another energy And of course, as it is part of the initial energy, it is less than the initial energy. And there is also emission of the electron from the orbital shells of the atom. So there is two particles that are emitted. So one particle is the just electron from the orbital shell, and another one is the gamma quanta with the energy less than the energy of the initial gamma quanta. There is dependence of the kinetic energy of the Compton electrons, means these electrons that are released due to the Compton scattering of the gamma radiation. And it depends on the, it varies from 0 to the maximum energy that depends on the initial energy of the gamma quanta. And as far as it is the range from 0 to this maximum energy, again, the spectrum, energy spectrum of the Compton electrons, it's not the discrete lines, but it is the continuous spectrum. There is again dependence of this cross-section or probability of Compton scattering on the charge of the matter, or every charge of the matter, and the energy of the initial gamma quantum. The third type of interaction, it's like a magic, because it is generation of two material particles, so it is generation of substance from the electromagnetic wave. So in this case, if the energy of gamma quanta is more than 1022 kiloelectron volts, it will generate two particles, electron and positron, that will move in different direction, and thus there is a generation of the substance or the matter from the no charge and no mass radiation. The probability of this or cross-section of this interaction depends again on the charge of the matter and on the energy of gamma quanta. Of course, the higher the energy of gamma quanta, the more probable that this interaction will occur, because there is a threshold for this interaction, and thus we need to the gamma quanta has to be higher than this threshold. And also it is interesting that for other interactions there is inverse relationship between energy and the cross-section, and only for this electron-positron pair production it is direct dependence of the cross-section and energy. And of course this emitted or generated positron will be further annihilated with the other electrons of the matter. There is a comparison of the cross-sections for different types of interaction of gamma quanta with the matter. So you can clearly see that the higher the energy of the electron, the more probable is becoming Compton scattering and then the electron-positron pair production. So that means that photo effect or photoelectric effect is more common for gamma quanta or for electromagnetic radiation with low energy. That's why for chemical analysis we usually use X-rays So it is electromagnetic waves with low energy, and in this range the probability of the photo effect is much higher than for other types of interaction. Also, this I have to note that these lines is just a 50% probability of the effect. So if we go to the left, it doesn't mean that in this area only photo effect is occurring, or in this area only Compton scattering takes place, or in this area is the electron pair, electron-positron pair production only occurs. So it just the 50% probability of these events, these lines. But it is important to note that for very light elements, there is no photo effect, almost no photo effect. The cross section is very low, and for the photoelectric effect. And the main type of interaction of gamma quanta with electromagnetic radiation is the Compton scattering. In all these interactions, we saw that, so in photoelectric effect, when we saw that all the energy of gamma quanta is transferred to the electrons. So there is no more gamma quanta. They are completely disappeared. In electron-positron pair production, there is also the gamma quanta disappeared to produce electron and positron pair. In Compton scattering, there is a release of the secondary electromagnetic wave, but this secondary electromagnetic wave further can interact with matter by photoelectric effect, for example. So that means that in all this interaction, the final step is the disappearance of the gamma quanta. And it is more effective to be disappeared in the case of the photoelectric effect. Thus, to stop the gamma radiation, we have to use materials that for which the photoelectric effect is more probable. And if we will look on this scheme, on this graph, we see that the heavier the material, the more probable the photoelectric effect. That's why, for safety reasons, to stop the gamma radiation, we use the dense material as we can find. And for many applications, it's just lead with the number 82. And we see that for this material, in a very broad range of the gamma, of the energy of the gamma quanta, the main mechanism of interaction is the photoelectric effect. That means the effective capture of the gamma quanta. There are another interactions, possible interactions of gamma quanta with matter. First of all, it is the Mies-Bauer effect, and the second is the photo-induced nuclear reactions, or just the photonuclear reactions. But we will not talk about them today. For electromagnetic wave, as I told you previously, there is no maximum range of penetration. The gamma radiation or X-rays penetrate or absorbed by the matter according to the exponential law. So we can see this exponential decrease of the flux of the matter, of the particles in the matter. And there is a dependence of the mass attenuation coefficients. So the higher this coefficient, the more effective the absorbance of gamma radiation. And on this graph we can see that this average mass attenuation coefficient depends or it is a sum of the attenuation coefficients caused by different mechanisms of interaction of gamma radiation with matter. So it is photoelectric effect, electron positron pair production, and Compton scattering. So this sum of these three components. And again, the more dense the material, the higher the mass attenuation coefficient, especially in the low range of the energies of the gamma quanta. And this is an example how different materials can have different mass attenuation coefficient. It is the very first photograph or picture that is made by Röntgen using X-rays. It is a picture of the hand of his wife. And we can clearly see that the soft materials like tissues, they have very low mass attenuation coefficient. Thus, the X-ray can easily penetrate through the tissues. But the bones, and especially the ring, as far as the average charge of these materials is higher than the charge of the just tissues, that means that they have higher attenuation coefficients. That means that they absorb electromagnetic waves more efficiently than just the tissues. And thus we can see that the darker the spot, the less X-rays go through the material. And there's just a clear example of how different materials absorb electromagnetic waves with different efficiency. And now the last particles that we will talk about today is neutrons, neutrons. And first of all, it is important to understand the classification of different neutrons because in further courses we will talk about the energy, nuclear energy. We will talk about reactors with slow neutrons, thermal neutrons, and fast neutrons. And so it is important to understand what we call thermal neutrons and what we are calling the fast neutrons. And this is actually just a dependence of the speed or energy of neutrons and classification of neutrons by their energy. And if we will look here, the thermal neutrons, they really have very low energy, and they call thermal because it is the average energy of the particles moving, and the particles had the same temperature as the surrounding environment. And this is quite low energy for neutrons. And cross-section of interaction of neutrons depends and inversely proportional to the energy or to the velocity of the neutrons. Why it is so? Because again, to interact, particles have to be very close to each other for a certain time. And if one particle is moving very fast, that means that the time for interaction is very low, is very small, and thus there is no enough time just for interaction. That means that the cross-section of interaction will be very low for particles that are going very fast. It is the same for alpha particles. We saw this dependence of energy losses, and for very high energies of alpha particles, the energy losses were very small. The same for electrons and the same for gamma quanta. The higher the energy, the smaller the cross-section of interaction or the mass attenuation effect. And the same is for neutrons. And all the neutrons that are produced in different nuclear reactions, nuclear fission, for example, initially they're all very fast. We should to slow down them for practical applications or for them to be captured. How we can decelerate or stop neutrons? Neutrons, as far as they have no charge, they have magnetic moment, but they have no charge. That's why the interaction with electrons is not efficient. Thus, the most effective interaction of neutrons with matter can be only when they interact with the nuclei of the matter. And we remember that it is very rare event. That's why neutrons can go through the matter with very high efficiency. When the neutrons meets nucleus, then they interact, and there is inelastic interaction, inelastic scattering, and the recoil nucleus will have some energy, and the neutron will also have some energy lower than the initial energy of the neutron. And we can calculate the energy that will be still with the neutron by this simple equation. And we see that this difference in initial energy and the rest energy will depend on the mass of the matter or the mass of interacting nucleus. And again, this energy loss will be inversely proportional to the mass of the nucleus. So A divided by A squared, let's say, will be 1 divided by A. That means the smaller the mass of the interacting nucleus, the higher the energy loss will be. So that means that the light elements are the best neutron moderator or neutron decelerator. There is a dependence of the neutron flux with the thickness of the material, and it is so the thicker the material, the less neutrons will go through it. And again, it is the exponential dependence of the flux on the thickness of the material. We can see how different materials decelerate and capture the neutrons, and we can see that in many cases the very dense material like lead, for example, more or less transparent for neutrons. So this is all for today. We talked about the interaction of different types of ionizing radiation with matter. I would like to say goodbye and see you next time.